Okay, so a new section, uniform continuity. In the previous section, we have seen that monotonic functions share many properties with continuous functions, but also there are some properties that they do not satisfy that continuous functions have. Now, next we come to this very important notion of uniform continuity. So let us start this section by considering one property of continuous functions. We have already seen that when a continuous function is defined on a closed bounded interval like this, where a and b are real numbers such that a is less than b, then f is bounded, and in fact f attains a maximum value and a minimum value inside this interval itself. That comes from the maximum principle. However, if we retain continuity but change this domain, then boundedness is not guaranteed. For example, if we consider this function where f of x is 1 over x, then this is not bounded. To see that, you can just simply consider you can prove it rigorously, but because we are simply discussing, we are trying to see what this notion is about. A graph is okay. So the graph of this function inside this interval is going to look like this roughly, where this is the point 1 comma 1, this is 1, and this of course is 0. Now the more you take x towards 0, the higher the value of fx will be. That is clear from the graph, and this happens without any bound. So the function loses boundedness in spite of being continuous at every point inside this domain. Okay, how are we concluding that this function is continuous? If you go back to the previous sections, in one of them we had the algebra of continuous functions. There we proved that if we take the quotient of two continuous functions and the denominator does not vanish at any point in the common domain, then the quotient is continuous. Now here the numerator is, both of them are polynomials, and we already know that polynomial functions are continuous. This one in fact is a constant function, and this is the linear polynomial x. Because x does not vanish inside this interval, so that's why this is continuous. Now, in spite of having continuity, we have lost boundedness. But what has gone wrong actually? We understand that because we changed the type of the interval, which is the domain, that this has happened. But let us look at this thing more closely. What is the definition of continuity? Let's go back to that. Suppose you have a subset x of R and a function from x into R, non-empty subset of course, and say x naught is a point in x. We say that f is continuous at x naught if for every epsilon greater than 0 there exists a positive real number delta such that the distance between f of x and f of x naught is less than epsilon whenever the distance between x and x naught is less than delta, and of course we have to also keep this in mind, because otherwise f of x may be meaningless. If x is not a legitimate input, if it is not coming from the domain, then f of x has no meaning. Now if we write these things not as inequalities but as intervals, then the same condition looks like this. Minus epsilon plus epsilon whenever x belongs to x naught minus delta comma x naught plus delta and x comes from x. So continuity means that you are able to control the output so that the output does not stray too far from f of x naught on either side. How far, that is determined by epsilon. By choosing x inside a region like this which contains x naught, so this region is, it has been called by the author an island of stability. This one. That is, you want something to happen, you want this to happen with the outputs. That will happen stably if you control the input and keep it inside such an island of stability. So what is happening to islands of stability at the points here for this function? That's how the section starts, and in fact it starts with an example. So let's see this example. This is the first item. And in this example we are not going to bound the function inside this domain, but we just simply consider this where x is positive. Alright, so let us now see what type of islands of stability we need at 2 points for this function. One of them is 1. Okay, so that means when we are talking about this, we extend this on that side a little bit. Say you consider 2 here in place of 1. That's because we now need 1 inside the domain. So what we seek, or what the author has done is, say we want the outputs to be 0.1 close to the f value at x naught. That is, our epsilon now is 0.1. Then what type of delta should we need for that? The author suggests that we can take delta equal to 1 over 11. Let's see actually how that is true. Suppose x belongs to, our point x naught is 1 now. This implies what? 1 minus 1 over 11 is less than x, which is less than 1 over 1 plus 11. I can leave this calculation part to you, but let's just see how it is that this delta works for this epsilon. So this means 10 over 11 is less than x, and that is less than 12 over 11. Because we have all positive real numbers here, we can take reciprocal, and that will reverse all the inequalities. This is greater than 1 over x, and that is greater than 11 over 12. Now we are interested in knowing the difference between fx and fx naught. This is fx, and fx naught for this x naught is 1. So let us subtract 1 from all the terms here. And that will imply what? 11 minus 10 is 1. So 1 over 10 is greater than this, which is greater than this one will be minus 1 over 12. And minus 1 over 12, it turns out, is greater than minus 1 over 10. If you find it a little difficult to suddenly understand this, you can of course argue like this. See, there is no need to memorize 100 formulas of inequalities to remember things like this. You just remember the basic rules and then get the things that you need by doing simple calculations. You want to know how this is true. 12 is greater than 10 because they are positive real numbers. You take reciprocal and that will reverse the inequality, and then you multiply by minus 1. That again reverses the inequality, and that's how you get this. Now, writing these inequalities in a slightly different manner, we get what? Minus 1 over 10 is less than this, which is less than 1 over 10. See, we have written minus 1 over 10 first, but accordingly we have adjusted the inequality in the direction also. Now, if we write in place of these inequalities a single one but using absolute value, then that gives us this. And remembering what these things are, we have simply got this f of x naught is 1, the reciprocal of 1 is 1, and 1 over x is the definition of fx, and this of course is 0.1. So you see that yes, for this value of delta we are actually getting what we wanted to get, and that is why at the point at the point 1, this is a legitimate island of stability. You can choose a smaller island of stability as well. Okay, that is your choice. However, what happens if we change this point x naught? If we bring it closer to the point 0, say now our new x naught is 0.1. This is much closer to 0 than 1 is. And say I keep epsilon same. Now what is my island of stability? The author says that now a new value of delta has to be chosen, and he suggests this delta, which is much smaller than the previous one, 1 over 11. And if you want, you can go through the calculation and see that now, let me just call it delta prime, say. Oh, now the point has also changed. No? It's 0.1 minus delta prime plus delta prime. This is a new island of stability around the new point 0.1. So what is happening here? Let's again draw the graph, this time more carefully, and see what we have achieved here in terms of island of stability. You see, the situation was like this. say this is 1, and here you have something say 2. Now if I roughly draw the graph, then it just looks somewhat like this. So what happens is that at the point 1, of course the function value is 1. Now if we want to keep the output values within the distance 0.1 from the value 1, say that distance is this much on either side. So this much is 0.1 and this much is also 0.1. Then I have this strip my x value needs to be inside this strip in order for this to happen. So here I have chosen some island of stability and where delta is 1/11. However, when we chose a much closer point to 0, so 0.1, here what is the corresponding function value? Now the function value is quite large. It is 10 actually. Now here if I want that kind of error tolerance, that is, if I still want the fx values to be 0.1 close to 10, now the output has changed. So you can see that now that strip is much smaller. Now your x needs to be in this region, so naturally your island of stability should also be correspondingly small, and this has happened here. So what is happening here is that as we are nearing 0, continuity is getting worse. In what sense? In the sense that in order to keep your output values within a certain distance, and that distance we are not changing, we are having smaller and smaller island of stability. That means the situation is getting out of hand. It is becoming more and more unstable as we are going nearer and nearer the origin. And that's what the author says when he says this statement, that continuity gets worse and worse as we near the origin. You see, geometrically continuity means what? I mean, at least for the kind of functions that we are seeing. You draw the graph is in one piece. As we are going near the origin, it's as if the graph is trying to break apart, break into two pieces. Here the increase is not that much, but as we are going near the origin, the increase is abrupt. It's as if one part of the graph is left behind and the other part goes up so sharply that it tries to break the graph. That's why continuity is getting worse and worse. However, this behavior is not exhibited by some functions. Let us now next see one such example. I mean, it's included in this example another function. So the thing we have to observe here, the main thing that we have to observe here is that the island of stability, of course, depends on this delta. In fact, the length of the island of stability is 2 delta. That delta, as we can see, it depends not just on epsilon, but also on where we are considering the island of stability, around what point. So delta depends not just on epsilon. I mean, if you change epsilon, delta will likely change. But not just that, it depends on x naught as well. However, if instead you consider this function, then say here without choosing any specific epsilon, suppose I choose any epsilon and I want the output values to be epsilon close to the output value at some specific point. I should have, I can choose the point now also after choosing epsilon. Say x naught is any point in 0, 2. I want this to happen. Okay. It means what if I use the definition of G? It means I have this. 2 comes outside using properties of absolute value and the fact that 2 is positive, and we can divide throughout by 2. Note carefully that here we are writing if and only if, not just implication, which means that in this case, now if I write these inequalities as intervals, we get this. So if and only if and only if, it is important, if and only if x belongs to what is delta? X minus epsilon over 2, x plus epsilon over 2. So here you see that unlike that case, in this case, the choice of delta, the largest possible, I mean you can choose a smaller delta also, but the largest possible island of stability comes from this value of delta. And very importantly, this does not depend on what x naught is. It's not a situation like this where the position of x naught matters, and if the situation gets even more bad, it gets even worse, then you have to choose ever decreasing deltas, smaller and smaller and smaller deltas. That's not the case here. This delta works for every x naught. So here the continuity is uniform, which is not the case here. Uniform in the sense that the same island of stability works everywhere. Not like this. And from this situation stems the definition of uniform continuity. You can guess that because of this strong condition that delta is independent of x naught, we will have many consequences. And that is true. Uniformly continuous functions enjoy many properties which ordinary continuous functions don't. So next comes the definition. uniform continuity. Let X be a subset of R and let f from X to R be a function. Okay, we say f is uniformly continuous. Sometimes we use this on X, sometimes we don't write on X when it's understood what X is. If for every epsilon greater than 0, there exists a delta greater than 0 such that the distance between f of x and f of x naught is less than epsilon whenever x and x naught are points in X for which the distance between them is less than delta. Okay, so now delta has been chosen for epsilon only. You see, we have not chosen x naught before choosing epsilon. Only after the choice of delta has been made that we are saying that this inequality is true for all x and x naught in X satisfying this, which are delta close. So in that sense, now delta does not depend on x naught and epsilon, it depends only on epsilon. Now the next item is a remark, and this remark asks us to compare the notion of uniform continuity with that of ordinary continuity. What is the definition of ordinary continuity? I mean, we have already seen it, we have written it also, but again, let's just for the sake of comparison, let's see it once more. We have a point x naught in X. We say that f is continuous at x naught if for epsilon greater than 0 there exists a delta greater than 0 such that this is true whenever we have this and x is in X. Okay. Now the first difference between these two definitions is that uniform continuity is not about anything at a point, at a single point. No. On X, on a region. Continuity, however, is a notion that is defined at a point. That is one difference. But of course, you can use this notion to define continuity of a function itself. Say a function is continuous on X. Okay, that also you can have. Then there is, then you don't have this distinction between the two where we are talking about one of them at a point whereas the other one is on a domain. Say now you have f uniformly continuous on X and say you have another function that is continuous on X. Then what is the difference? then the difference is that in continuity, delta depends on the choice of x naught as well as epsilon, whereas in uniform continuity, delta depends only on epsilon, and that same delta works for every x naught. The island of stability retains its size, does not matter where it is. Where it is, of course, is decided by x naught. So that is the remark. Alright, now you can understand that we cannot hope to use this definition itself to decide that a given function is uniformly continuous. So we need to formulate some tools that will enable us to do that decision for us. So what type of tool can we develop so that we can quickly say, using some sort of theorem that involves that tool or that notion, that a given function is or is not uniformly continuous? You have seen whatever we have gone through so far in analysis, we have always tried to somehow relate it or formulate it in terms of sequences, and this time also we are going to do that. For example, for continuous functions we have a sequential formulation. For uniform continuity also we will have a sequential formulation. However, before we go to that, there is an informal example, and in that example we go back to that reciprocal function. I think the author is calling it f. This function is continuous but not uniformly continuous on 0, 2. It's only an informal example. I mean, there is the word informal that comes after this. That's because it's only a statement. We will prove this, but not using definitions. We have only guessed, looking at the bad behavior of this function in that graph, that we guess that it's not uniformly continuous. However, we will prove it by other means. So now comes a notion next, which we have already seen in a way before. And the notion is that of equivalent sequences. Do you recall that when we constructed the real number system from the rational number system, that time we considered equivalent Cauchy sequences of rational numbers and used that equivalence to give some objects which we called real numbers, formal limits. And the setup was such that two equivalent sequences, Cauchy sequences of rational numbers, give the same formal limit. I mean, it was defined in that way. Now we are going to define something similar, but not just for Cauchy sequences of rational numbers, but for any sequences of real numbers. So that is the next item. This is definition 995. Okay. And we are going to do it in steps first, and then we will write the the definition at once. This style of presenting the definitions in a somewhat unconventional manner, where we gradually increase the complexity. This is done by tau to improve readability and also to improve understanding. That is, he defines something at first which is not the entire thing and then makes it more and more complicated. It's not a usual practice, but it helps sometimes. Let, it will become clear what we mean by that. Let M be an integer and let an and Pn be two sequences of real numbers. Oh, we will need one epsilon also. We say that they are means the sequences are epsilon close if we have this, that is term wise the terms are epsilon close to each other, the corresponding terms for all n greater than or equal to m. Next we say that this is how it becomes gradually more complicated and it goes towards the actual definition of equivalence. We say that they are eventually epsilon close. If there exists an integer n which is at least m such that from the experience that we have with this kind of things, you can guess what I'm going to write next. Next we will have these inequalities, but not for all n, but for all n starting from capital N, because eventually. And finally, we say that they are equivalent if okay. I actually wrote this condition. No? We can write it in terms of this previous one. Okay, actually that's how the author has written it. How foolish. Yeah, if I'm again writing everything, then what is the point of doing it in steps? If there exists a such that these two sequences are epsilon close. And which of course means what I wrote there. And finally, we say that they are equivalent if they are eventually epsilon close for every epsilon greater than 0. Now if we combine all these things, I am not discussing this again, okay, because we have seen this kind of things before. If we combine all these things and write the condition for equivalence of two sequences at once, then this is how it's going to look. AN and BN are equivalent if and only if for every epsilon greater than 0 there exists an integer n which is at least m such that this for all n greater than or equal to n. In fact, by now we are more used to writing things like this. That's because we have already seen these things, but it's not purposeless. We need some time to get used to these things, so that's why it's given in steps. So that is the notion of equivalence of sequences, which is actually not exactly something new. We have seen this before, but in a restricted situation, only for Cauchy sequences of rational numbers. Now, however, it is for any two sequences of real numbers. Now, this notion of equivalence of sequences can be linked to uniform continuity, just like convergence sequences are linked to ordinary continuity. But before we see that link though, we need some way of deciding whether two sequences of real numbers are equivalent, not using the definition, but we need a result. So that's where the next lemma comes. Oh, but before the lemma there is a small remark also. This remark arose in a previous situation as well, and the remark is about this epsilon, whether we should choose epsilon to be rational or real. We have already gone through this kind of discussion before, and we saw back then that whether we take a real epsilon or rational epsilon, ultimately there is no distinction, essential difference. But for us, epsilon will in general be real. And in a similar manner, whether you use strict inequality here or ordinary inequality, it does not make any difference in the end. So this remark is just about that. Instead, let us see the lemma. Let AN and BN be sequences of real numbers. Then they are, and we are not restricting these sequences in any way. they are not necessarily convergent or bounded or anything, Cauchy nothing, okay, just simply sequences of real numbers, then they may be divergent also. They are equivalent if and only if this limit exists and is equal to 0. Two divergent sequences may also be equivalent. Okay. So we can use this condition to see whether two given sequences are equivalent. And the proof of this is the first exercise. So we will see the solution in the community section. Alright, but now we come to our main thing, which is the link between equivalent sequences and uniform continuity. So this next item is a proposition. Step 8. 7 was that one. Let X be a subset, non-empty subset actually of R, and let F be a function from X into R. Then the following two statements are equivalent. Yeah, statements are equivalent, sequences are equivalent as well, but different kinds of equivalence. F is uniformly continuous on X. That is the first statement. And the second statement is this: whenever an, the author may have chosen 0 or 1 here, ultimately it does not matter, let me just write n. This and Bn are equivalent sequences in X. That means the sequences are having terms which are elements in X and they are equivalent. If we have such a pair of sequences, then the sequences f of an and f of bn are also equivalent. That is the second statement. So the proposition claims that if any one of them is true, then the other is also true. Then the sequences this and this are also equivalent. So this is a necessary and sufficient condition for a function to be uniformly continuous. We can compare this result and the sequential formulation of ordinary continuity by saying this: a function is continuous if and only if it preserves convergence of sequences, and a function is uniformly continuous if and only if it preserves equivalence of sequences, pairs of sequences. And the proof is, for the proof we will have to see the second exercise. So we will see these things. And that's just it for tonight. In the next analysis video, we will see what comes after these things. Because this is a strong notion and an important one, we expect to see many consequences, and there are many nice consequences. And besides this, tomorrow of course I will upload that calculus video that for some reason I did not do this week. So that's just it. See you tomorrow with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.